Okay guys, I'm doing this one a little bit different this time. I'm always talking about doing homework. Do your homework before you get to a vehicle. And right now I'm in my dining room at home and I'm getting ready to leave to go do a job. This is for Arlington Auto. And what I'm working on, or what I'm going to be working on, is a 2008 Saturn Vue with a 2.4 liter VIN P as in Paul, VIN P engine. What they have done so far is they've scanned it for a trouble code and they called me, and so what I typically do is I'll get a wiring diagram for the PCM, and then what I will do is I will pull up the flowchart for the code, and this is just really arming myself before I get there. And so the code we have in memory, let me get you zoomed in on this page here. Code we have in memory is a P0013 trouble code. And looking on this chart, we can see that a P0013 is an exhaust cam actuator solenoid control issue. So it's the exhaust camshaft actuator solenoid that is setting this fault code. My thoughts going into this: I don't know anything about this vehicle. I've never worked on one. I want to know how this solenoid is controlled. A little bit of preliminary stuff. Just the fact that it has a cam actuator solenoid tells us this is a variable valve timing engine. Using this flowchart as a guide, which I've said to you guys in the past, you know how much I hate flowcharts, but I'm using this as a guide. And in this flowchart, this circuit description, it tells me a lot about this solenoid. It says the control module sends a pulse width modulated 12-volt signal to the camshaft position actuator solenoid. What that tells me, this is going to be a power side switched solenoid. Very important in troubleshooting wiring problems, knowing that. A little side note, for more on power side and ground side switched solenoids, this will be section 3 in my book that you guys can refer to. Conditions for setting this code. This is important to me because I want to know if this is an electrical problem, is it a hydraulic problem, and so on. And what we see is it says if the ECM detects an open short to ground or short to voltage on the high control circuit, or an open on the low reference circuit for more than 0.25 of a second, that would be the conditions for setting the code. So there you go. This is going to be a wiring issue or solenoid issue. Not really too much worried about the hydraulics or any other sensor. This is going to be a trouble code that's just associated around the controls of this solenoid. So this should be a pretty simple job. And again, going into this, it's power side switched according to this. Pulse width modulated, meaning an on-off signal. What else did I want to point out? Well, let's look at that on the diagram real quick. It's a 2-page. Normally I have these taped together for easier viewing. This is what I like about Mitchell wiring diagrams. They put the whole computer system out on a couple of pages. And what you'll see here, I color coordinated these already. And what you see is my exhaust camshaft solenoid is right here, and my intake camshaft solenoid is here. So focusing on the exhaust, that's our trouble code. The yellow and orange wires that I've highlighted, notice that they both go to the computer. Now what I say in section 3 in my book as far as identification goes is you follow the wire that doesn't go to the computer, will tell you the circuit design. If one of these two wires goes to a ground, external ground, that means it's power side switch, meaning the other wire going to the computer would be power. If one of these two wires would be going to an external fuse, that means the wire going to the computer would be ground side switched. And in this case, we cannot make that identification using the wiring diagram. Both wires go to the computer. Now in the past, what I've said is every time we see this, it's a power side switch circuit. So you might be thinking, why do they run the ground wire to the computer? Well, it's for better monitoring of the circuit. And I think the diagram or the flowchart actually says that. Show that to you again. The computer is monitoring both sides of this circuit. If an open or short to ground or short to voltage on the high control circuit, remember it's power side switched based on this description up here. I know we can't see it on the diagram, we can see that up here. Confirming what I'm telling you, that when you see both wires go into the control module, they're power side switched. There's a variable to that, I'll get to that in a second. The reference, low reference, which is another name for a ground, is also monitored. So that is why it's being done. When they put both wires to the computer on a solenoid, it is for more accurate diagnosis. So let me back up. I said when you see both wires go into a computer, it is power side switched in all applications that I've ever seen. Now there's a twist to that. Gas direct injection systems, which I just covered on my premium channel. I uploaded some stuff on gas direct injection. The injector control wires, both positive and negative, go to the computer. However, they're both controlled. Both the power and ground are controlled. So we need to be careful when it comes to manually energizing these kind of circuits, because there are variables to them. Now we'll see what this entails when we get to the car as far as manually energizing the circuit, or if I have bi-directional controls on the scan tool. I don't know yet if I will or not. Last piece, and then my next shot here will be on the car, is using this flow chart. Just want to point out a couple of things. Maybe this will be better done when I get to the car, but this is doing your homework. This is what I did previously before filming this. This is what I do before I go to any garage that I'm unfamiliar with the component or system that I'm working on. Gather information. So we have system verification. This would be the whole system that I can bi-directionally control. At least, with a factory scan tool I can do this. It's telling me to command the actuator on and watch for the camshaft actuator parameter to change. Now, again, that's potential. I'll be able to do that. Just because it says it here doesn't mean my scan tool will have that option. So hopefully I can do that. There's some other stuff about checking oil level and things like that. Of course, we want to do that on any VTEC or variable valve timing system. But again, this code that's being set is associated with the solenoid. So, we want to do these system verification procedures as a preliminary really to any diagnosis on these systems, but we're focused on the solenoid. So down here, what do they have us doing? Further confirmation that the computer is power side switching this. If you look at step 2, it says test for less than 5 ohms between the low reference circuit. Again, that's a ground, terminal B and ground, and it should be less than 5 ohms. So what's that tell you? That tells you the one wire is constantly grounded inside the computer. Pretty typical power side switch circuit, you'll see that. So let me cover this flow chart real quick, and you'll see how crazy this one is. Step 1, ignition off, disconnect the cam actuator solenoid connector and test for resistance on this low reference to ground. It should be a ground. That's what step 2 is telling us. Step 3 is to take a test light and put it between the terminals. So that would look like this. What they're telling you to do is to take the solenoid, disconnect it. So disconnect the solenoid. Let me back up. Step 1 was to take an ohm meter. So step 1 was to take an ohm meter to ground and measure the resistance of this low, what they're calling low ref circuit. That's your ground inside the computer for the solenoid. It should be less than 5 ohms, right? It's telling you that that has a good ground. Step 2 was to take a test light between these two terminals like that and make sure the light does not light. If the light lights with just the key on, engine off, they're telling you to check for a short to voltage in this positive circuit or a shorted computer that's constantly turning the solenoid on. So not a bad test. All right, continuing. Step 5. You know, the other steps in between would be repair the circuit, replace the computer, depending on what you have. Step 5 tells us to command the cam actuator solenoid on with the scan tool and verify the scan tool cam solenoid circuit short ground test status is okay. So there's some kind of data PID that we can look at for a short to ground. And I'm not going to do this one. All I need to do is do my checks with my scope for that signal. Step 6, I got a question mark here. This is crazy. Install a 3 amp fuse jumper wire between the control circuit terminal A and the low reference circuit terminal B and command the cam actuator solenoid on with the scan tool and verify the scan tool cam solenoid circuit short to ground test status is now fault. Remember up here we wanted it to say okay, and now it should say fault. If it does, then we replace the solenoid. Guys, listen, that is crazy. What they want us to do in this flowchart is to take a fused jumper wire from here to here, okay? So you got a fuse in the middle of the 3 amp fuse, which is not going to be in place to protect the computer. That's going to be in place in case there's a short in the circuit so we don't burn up the harness. So we're taking a jumper wire from the control to ground and we're commanding the driver to turn on. We're intentionally shorting the circuit to ground, power side switch circuit. Kind of crazy that they'd have you do that in a flowchart and then look at a scan data PID to say fault. And if it does, what that tells you is the entire circuitry is good, and then we change the solenoid. That is a crazy test. I'm not going to do it this way. Just wanted to show you the manufacturer flowchart. A lot of you guys are concerned about me using my test light in ways that I do it. And guys, listen, my test light's about a 200 milliamp bulb. This solenoid carries way more current than that. How do I know that? Without even knowing this car, I'll show you. One last check on this flow chart right here. This solenoid should be 8 to 12 ohms. That solenoid is going to be very, very near 1 amp of current. Way higher than my test light. And again, you talk about circuit protection. A manufacturer flow chart has you shorting the control wire on a power side switch circuit directly to ground. Remember, this low reference is ground all the time. That is crazy. Pretty cool, all the protection they have in here. This should be a very easy one. This introduction is most likely going to be longer than the actual diagnosis on the car. So let's go to the garage now. Shot of the car I'm working on here. Like we said, it's a 2008 Saturn Vue. I'm going to take you inside of the scan tool now. Okay, I'm going to read the trouble codes just to show them to you. You see we have a P0013 exhaust cam position actuator solenoid fault. Let's go back, and what we want to do is see if this gives us those bi-directional controls, and I did check it already. It does, and it's listed under camshaft actuator tests, and we have 2 methods. The camshaft position actuator test gives you a variable percentage where you can command the solenoids on and off and look at the movement of the cams, and the camshaft position solenoids test is just an on-off test. So really what we're going to do is this one first, and when we go under the hood to do our electrical checks, we'll probably most likely use this one. So going to the actuator test, we'll do the exhaust cam first, and it tells me make sure the transmission's in park and make sure the parking brake is set, block the drive wheels. All of that is done. So hit continue, and it just heard the RPM rise on its own. And what I'm going to do is a custom list here for you, and I'm picking all of the camshaft data through the RPM in there for you too. And what we want to do, this one is the exhaust cam. So I'm going to hit start, and when I command the actuator to turn on, so we have a percentage here, there's 5, 10, you know what, let me use the stylus, get my fingers out of the way. So I've just commanded 15%, you see the desired is there, 15. The variation is there, this variance, meaning the computer really wants that to be 0 all the time. The actual angle is 0, it hasn't moved. There's 20, and then according to our flowchart, 25% was the most we can go, and it in fact is. And it just kicked me out of there, would not let me go any longer than that. Let me show you the intake cam one now. And maybe we'll go back and do the exhaust one again, make sure we got all the data we needed. RPM just raised on its own, custom, deselect. And this is going to be the intake now, so we want to watch this side. Hit start. And I'm going to command this intake cam actuator now. You see the command that I've picked is 15. Actual cam angle's 15. Our variation is 0, meaning that's good. The command matches the actual. These are good numbers. The percentage here, this would be the duty cycle that you're looking at. This command percentage is 37%, and it just timed out again. All right, so a little lesson on duty cycle there is duty cycle percentage, as I've said many times in other videos, does not match actual position. It's the percentage of valve command, not position. Keep that in mind. But you saw with that test that the exhaust cam had no movement whatsoever. And so what we need to do is go under the hood and check it electrically, make sure that our wiring is good, make sure our computer is good before we condemn the solenoid. Well, they made this really easy. Just a little plastic cover I had to take off, had to take the air cleaner off, no big deal. And the two actuator solenoids are right here. And let's see if I get you a shot of this. It actually says exhaust right here on the valve cover. Says intake right here on the valve cover, so I know exactly which one's which. Now, of course, a little bit of thinking here too. You know, the front is where the intake manifold is. Another method obviously would be this is the intake cam as noted by the intake manifold sitting right here and the exhaust manifold back here. This is your exhaust cam, but it's nice, it's stamped on there. Our focus is going to be on this one right here. We're not going to check this like the flow chart told us to. We're just going to do some voltage measurements. I have a scan tool that I can bi-directionally control it. We'll see what we got. So we're about to do a voltage measurement, and this measurement is going to be critical in direction. So as I've stated many times, first thing we want to do is check our meter. And I put my ground up here on the firewall because the battery is not easily accessible. Pop this little cover off this distribution box, and I'm just going to touch a known battery positive source. So just touching a known battery positive source right here, making sure that my meter is reading 12 volts. Take it off, put it back on. So what's that tell us about our ground location? Ground location is good, and we can rely on our meter. So now to check this solenoid. So we've done our homework already. We know that it is power side switched. We know it is a pulse width modulated signal. So our first measurements here, we don't expect with the key on to see any voltage on either wire. And before I do this measurement, let me just talk about this for a second. It is very common when you have a solenoid failure that when you start back probing and moving connectors, that the solenoid will actually come back to life because you've really momentarily fixed a problem internal just by touching it. Very common. Not sure that's going to happen. I actually hope it doesn't happen, because what that'll do is make you guys question really my diagnosis here. But we're going to do our measurements first, see if I can get you a shot of the meter and my test at the same time. Okay, first measurement. Going to go after the yellow and black wire. And again, I don't expect to see anything. There's 0.9 of a volt, maybe some type of a bias voltage that's there, possibly, I'm not sure. So 0.9 on that one. And looks like maybe a black and white wire. Tough to see with this conduit in the way. And that is my other wire, a perfect 0 volts. Pretty confident that that is my ground wire. I'm going to go back to this wire that read 0.9. There it is. A nice thing here too, on this car we have 2 of the same solenoids, 2 of the same circuits. We know the intake side works. So I'm going to do a quick measurement over here just to see if that's a normal voltage or not, this 0.93. My guess is it's not. And that we're seeing an elevated voltage because the solenoid's open, although it could be wrong. Okay, here's one side of this intake solenoid. 0 volts, perfect 0 pretty much, which we would expect with no current flow. And this would be the other wire on this intake solenoid. And I got a perfect 0 on that one too. So what that's telling me, before I really go any further, is this exhaust solenoid is open. That 0.93 that you're reading is a bias voltage, and I believe I can prove that. If I unplug this intake solenoid and create an open, I believe what you'll see is that control wire, the positive control wire, is going to go high, and I believe it is the... I can't see these colors too well. It looks like maybe a pink and black on the intake side. I'm going to go back on that wire, and then what I'm going to do is unplug the solenoid to create an open. I'm going to get that lock-in clip out of the way. All right, so this is going to be intake solenoid unplug it test. I'll bet you we see the same 0.93 of a volt. There's that 0.9395 of a volt bias, proving what I just said. This exhaust solenoid is definitely open. So it would have been nice reviewing that flow chart that we did earlier on this if the manufacturer, all they needed to do was say, hey, check for a bias voltage of 0.9 on the control wire, and that tells you the control circuit integrity is good. Not that crazy test they were telling you to do. I'm going to show you the signals anyway. There you go. There's that bias plugged in. Drops to 0. That is a good solenoid. What I'm going to do is show you, well, I'll stay on the intake side here for a second, and I'll command it on with the scan tool and show you the voltage change. The test I'm going to do is the solenoid one, just the on-off. I'm on the intake side, and see this one's done with the key on, engine off, different than the other one, which is what we want. It's all we need. And we don't care really about these data PIDs. We just want to turn it on up here while we're looking at the signal over there. So I'm going to do this. Oh, come on. Device exceeded. That's ridiculous. It may make me cycle the key on and off to do this again. They put these timers on these output devices. Some of them don't need to be timed. Yeah, see, it's not going to let me. I'm going to have to exit out of here completely and turn the key off and back on again. Go back in and do this test again. It's these generic timers they run. All right, so you saw what I was doing here. I'm going to focus you on the meter so you can see the signal. And I'm on the control wire. Remember, the control, it's power side switched, and it's pulse width modulated. So what we're going to see is a up-down signal on here. It's all we're looking for. There it is, right there. Turn it on, turn it off. That's good. All right, then the other thing you want to do, man, that timed out again very fast. So you saw the signal on the feed. The other thing we want to do is we want to check the ground, and the ground would be a loaded circuit test. It's not loaded unless we're commanding the solenoid on. So we get on our ground wire now. That's grounded by the computer, and we're going to redo the same tech again. I may need to cycle the key on and off. Doing the intake side, the known good one first, then I'll show you the other side. The rest of this really isn't needed. We're pretty much done. Turn this one on. Nope, it's going to make me cycle the key. Cycle the key on and off. And what we're going to do is a ground-to-ground voltage drop test with the circuit energized. Turn the circuit on. You see a little voltage rise there. That's good. We want to see that. So that's how you check it, bi-directionally. That's a good ground right there. That is a good control. We definitely don't need to be jumping wires together like the manufacturer flowchart has us do. That bias voltage, I think, was key for this. You saw on this positive wire that this 0.9 of a volt signal, get you back on the exhaust side. Oh, that's crazy. Now I'm reading 2.44 volts. Let me exit out of here. Cycle the key. Well, that's a different number than we had before. Wonder why. Let's try the exhaust one. Turn this one on. That's a straight on signal. No pulsing there. That was weird. Exit. Cycle this key one more time. See, I don't like that 2.44. I'm not sure of the computer logic there. That wasn't there a minute ago until I started these bi-directional tests. This isn't changing the fact that I need a solenoid, guys. Just trying to figure out the controls here. Working on something new. See, my ground is good and steady. So no question the ground is good here. If you think about this, if the ground was open, that would act as an open solenoid, and we would have seen that 0.9 of a volt on the control wire with an open ground. I'm not worried about an open ground here. I don't like this 2.4. You saw it went up to 12 when I commanded it. It was not pulse width modulated. This is probably logic in the computer for this trouble code. And what I'm going to do is clear this code out of here. See if this changes things a little bit. Codes are cleared. Yeah, it almost seems like, you know, the computer's checking the circuit. Almost raising, I don't know if we want to call this one a bias or not, raising the voltage. I know the controls are good. Let's go back to, you know what I can do is I can simulate a good solenoid with a test light. Hold on one second, let me do that. So what I'm doing with this test, I know this solenoid's open, guys. I'm gonna go test light to ground, check my light, make sure it lights. Okay, good. And then I want to trick the computer into thinking this solenoid is good. And what I'm doing is just taking my test light on this control wire to ground. That's going to pull this voltage to ground. You see that it did. Of course, my light did not light. And there's some kind of circuitry in here. So what I'm going to do is, let me get an alligator clip for my test light. All right, so this 2.4 volts, I think we can call this a bias. I don't know why the bias changed. you know, it was within me activating the intake side. I came back to the exhaust side and this changed. You saw when I did the intake side, unplugging it, that 0.93 showed up, same as I had when I started here, telling me I have an open in the circuit. Ground was good. If the ground was bad, voltage would have been high. It was not open solenoid. We're not deviating from that. What I'm trying to do now is just to prove that, you know, this is really computer circuitry that's checking this thing. And I'm going to do it with a test light connected to ground. And what this test light's going to do is just simulate that there is some connectivity to ground through a solenoid. Now, it's not really a solenoid, it's my test light. And the current flow is going to be off here, but this will, should keep this code from coming back immediately. Let me clear the codes again. Let's display them, see if that code came back. It did, immediately came back. So let me now clear it with my test light there. It's another way you can prove things, is just being a little bit creative. So I cleared the codes. I'm going to display them again. No codes present. Let's take my test light off. And let's go back. Reread them. Look, immediately code came back. Put our test light back on here. Come back up here. Clear the codes again. This is pretty cool. It's another way you can verify circuit integrities using scan tool data, using trouble codes. Signal circuit integrity, that's the chapter I'm thinking of in my book. I think it may be chapter 10 or 11, where I do signal circuit integrity testing. That's really what I'm doing here. This is with my test light there. Notice the code's gone. Again, I'm not worried about our wiring here, guys, at all. What I cannot explain to you is why that bias voltage increased. But what I will be able to show you now is this actuator test. Go back to functional. And my suspicion, when I do this exhaust one, it's really fast. This generic timer times out fast. So I'm going to keep you focused over here. My suspicion is what I'm going to see here now is a pulsing like I saw on the intake side. The reason it was not doing the pulsing is the computer knew there was a fault and just reacted differently with this test. So here goes the test. Hit continue. And the test light may actually light here too, but our focus is up here more than it is the test light. And we'll turn it on. There is our control. That test light is lighting. Turn it off. That's pretty sweet. So nothing wrong with the circuitry here, guys, at all. I could jump over and show you the ground wire too, but I'd have to cycle the key again. You know I should, because some of you guys are going to question it. I'm telling you I don't need to check that ground. If you guys are paying attention, here's why. I don't need to check this ground again. I did already, but I don't need to check it again because when I started I had 0.93 of a volt on this wire. If I had a bad ground causing this solenoid to not work, I would have had that same 0.93 of a volt bias over here on this ground wire. I did not. So it told me the solenoid is open. It's exactly what we have. For the naysayers, I'll redo it. Ground to ground, loaded circuit. It's what we want to do. And there's multiple ways we could do this. I could actually just take my test light, switch it to battery positive. In fact, I'll do that on this one. Oh wait, you're gonna hurt that computer. No, I'm not. There it is, right there. Test light to battery positive. I'm just touching on the post. Test light is lighting. Where's that ground at? It's inside the computer. But wait, you shouldn't ever use a test light on a computer circuit, right? Wrong. Solenoid draw is probably over an amp. Well, it's pulse width modulated, so we'll control current flow, but is my 200 milliamp test light going to hurt this circuit? Not at all. Think about the flow chart. The flow chart wanted me to jump the signal or the control and the ground together and then check for a fault. Yeah, I don't want to do that. I'm not going to hurt the circuit here, guys. The voltage reading, got to cycle the key to show you that. All right, key off and back on again. And I'm going to actuate this solenoid. This will be the voltage measurement. Again, not needed, but I'm showing it anyway. I want to see a voltage rise here of a little bit. Although, you know what? We're not going to. Why? Because the solenoid's open. So here, turning it on now, no change at all. Why didn't we get a change on that ground? We didn't get a change on that ground because there's no current flow on this solenoid. We are done. It needs this exhaust camshaft actuator solenoid. So I'm going to tell this garage to put one of these in. And no question about it, we're good to go. Remember the bias voltage on these? Power side switch circuitry, bias voltage. Section 3, I have this information, bias voltage. It's really, really cool that we can use this for a diagnostic purpose. And you know, it's a shame the engineers don't give it to us. 0.93 of a volt is the bias voltage that I saw on the intake cam. Let me show it to you one more time. Back probe the intake cam. Solenoid, sorry, I'm calling it the cam. All right. Notice the steady 0 volt. Unplug the connector. Oh, there's 2.4 volts now. Well, it was at 0.93 before. What changed? I don't know. Maybe my ground connection on my meter? I don't think so. That bias changed on me. It was 0.9 before, and now it's 2.4. And it may have to do with fault codes in memory and it changing things. Well, maybe that's why the manufacturer's not giving it to us, because it's not consistent. But that right there, guys, that's unplugged. And keep your eye on both. That's plugged in. That is a bias voltage that's used in this circuit. And if you know about it, think about this. Why would you do opens and short circuit testing on a harness with 0 volts, say, all the time, when all you have to do is come under here and unplug it and look for a bias? If that bias is there, how's the computer, how's the wiring all the way down? It's good. I mean, that's the idea with this. Get used to it. Start looking for it. It is a huge advantage. There are variables with it. You saw one. Why did it change from 0.93 to 2.4? I'm pretty sure it has to do with the trouble codes that are being set. I'm not 100% sure on why it changed, but it's certainly useful, and you saw all the checks involved with this exhaust actuator solenoid. No question about it, needs that solenoid. Okay, I was playing around with another car while I was here, and they put this actuator in while I was working on that other car. I didn't think I was going to have the opportunity to show you guys this, but I'm going to show you the fix. This is our faulty actuator, and what I'm showing right now is no codes present. And I'm going to go back and we're going to redo this actuator test that I started with, and it's going to be the one where we change the percentage and already raised the RPM. And we'll just focus on these ones right here, these first 3, as I hit start and then I change the percentage. We want to see a corresponding change on the camshaft. You see the angle change, 10%, 10%, a variance of 0, that is a fix. 15, there's 20, 20% exhaust cam angle, or 20 degrees, sorry. 20 degrees, I was saying percent before, I apologize for that. 20 degrees, and our timer just kicked us out. Apologize for misspeaking there, but that is a fix. I wanted to show you guys that. I know some of you really want me to do more of these, and I don't always have the opportunity to. You know, I'm at these garages, and you know, I do my diagnosis and I get paid, and then I go home. So, you know, I'm not always around for the fix, but whenever I can show you, I will for sure. And you know, a lot of different testing methods and procedures in this one, as usual, and I know you guys like that. So appreciate all your support, and I hope you guys like that one.